Hi. Hi. Aha. Hi, Lizzie. Hi, Maisha. Hi, May. Hi, John. Hi. That is right. Yes. Hi. Okay, that was my visuals. Hi, Maisha. Hi, May. I said May. Oh, hi, May. Hello, Eric. Oh, I didn't even see her. I'm sorry. Yes. Hello, Eric. Sorry about that. Hi, Liz. Hi, May. Okay, now it's getting crazy. Hi, May. Okay. Hi, Jayla. Good afternoon, Noel. Awesome, Jayla. Awesome, Noel. Hello. Okay, now I'm not gonna get into that craziness. Hi, John. Okay, more people coming. Thank goodness. Okay. Hello, hello. Hello, Elizabeth with an S. Good to see you. Why did I want to say? Oh, okay. And one quick thing, guys. So it's great to see you all as usual. Great to visually see Lizzie, for example. And one thing reminder. So I'm still very behind on turning back a lot of things to you, but I have been turning back the game turn assignments. And please, there are many of you who have been doing a lot of things. I know, participating and showing video and this and that. And please remember to submit for the points. I mean, you might as well get the points for it. Like, I mean, for example, on some, there are a couple of you who like in game turns, like in the regular game turn, like pointed out that today you showed video or today you asked a question with your voice or something, but please put also like double dip and triple dip. Like I won't remember to give you all the points unless you also put that in. You know what I'm saying? Just don't forget, like there are these forms of participation that you guys have been doing, and I totally appreciate. And some of you even note it in one place, but please note it every place that you can get points. But okay, hi, oh, and hi, hi, Lizzie. All right, I thought she had already said. I already said hello to her because I saw the video. But okay, yes, hi, and she's saying hi to me. Okay, you guys are funny, and that all counts as multiplayer co-op too. But okay, let's do some physics here. I want to, yeah, so I want to do some physics for a change. But so I have notes for today and everything, but I know that, excuse me, I know that I sort of ended abruptly on Monday. The clock ran out a little bit earlier than I did. So actually, I would like to very quickly, like I have notes for today, but please indulge me. I want to go back to the notes that we were taking Monday, and I want you to help me tell me. I think I know where we left off, but I could use your help in telling me exactly the last thing we actually explained in the notes. That is to say, I'll tell you what I mean. So I'm going back to Monday's notes for a minute. I'm going back to, and I believe, well, this is what I want to know. Monday, we were going over the homework. We were going over homework number 2. Excuse me, that's gross. I believe, what I want to know is, we did this, I believe. This is part B, question 1. I believe we did this. I believe we talked about it. I believe, oh, I know we did this. This is, we went over part C of question 1. Again, I'm talking about homework 2 here, math methods. Stop me when I'm wrong, but I believe we talked fully about Roman numeral 1, question C, the whole, is it a solution or not? And this was the Maisha question, as I recall. She asked, what does it mean when we say, is it a solution? And we did this whole question C as a counterexample to show where something is, and we're up to, okay, thank you, John. Oh, that was a very helpful, serious thing for John to say. Thank you. So we're up to D. Okay, thank you, John. So we're up to D. Okay, we're up to D. Okay, thank you. So that's this right here. Okay. That's great. Thank you, John. I do appreciate it. I can't even make a joke about that. All right. So we're up to D. What I'd like to do, so I'm going to stay on yesterday's notes for a bit. I mean, for whatever it's worth, I mean, you have the PDF of this, but so again, for anybody who's tuning in now, we're talking about, I mean, please be looking at whether you've handed it or not. We're talking about homework 2, math methods. We're talking about Roman numeral 1, the derivatives. We're talking about part D here. And yeah, part D, like John just said, okay, part D, written here on the screen. Part D is just the justification or the sort of steps that we really had to do for part C in order to show that x equals a cosine 5t is not a solution to d2x dt squared equals negative 3x, right? So, I mean, I know this is all obscure because it was 2 days ago, but question D is really just asking you to go through the exercises, taking the two derivatives that you'd have to do in order to realize the answer to part C, which was no, which we did, okay? So that's D. D is in the middle of the page here. Then I move down to E. Okay, similarly, E, I'm not going to spend a lot of time talking about E also, excuse me for 1 second. E also is somewhat straightforward, I hope, at this point. Like, E is just giving you a function. It's asking you to take 2 time derivatives of it. And it looks like the same function we've been differentiating over and over again in this homework. The only difference is that E, now instead of writing omega, it's writing the square root of k over m, right? In other words, now in E, we're actually specifying that the kind of oscillator that we're talking about actually has a mass and actually has a metal spring of stiffness k. Like, everything up until this point has been all the questions in the homework to this point have been about the general mathematics of simple harmonic oscillators in general. They might be a mass on a spring, they might be a bob on a pendulum string, they might be a temperature system oscillating harmonically. They might be some electrostatic field magnitude oscillating. They could have been about anything. And for any of them, omega squared referred to whatever constant of proportionality was right there in the differential equation. Omega was the square root of that, was the angular frequency of the oscillator in general. Now here we're just being specific and saying, oh yeah, like what omega comes from, what omega is determined by is K and M. If what we happen to have is literally a stiff spring and a piece of mass at the end of it, okay? So in other words, omega squared is the constant of proportionality no matter what your oscillator is. Omega, the square root of that, is your angular frequency no matter what your oscillator is. But what actually determines that angular frequency, what actually determines that omega squared, it's the specific parameters of the specific physical oscillating system that you're talking about. In the case of a mass on a spring, omega specifically is square root of k over m. Okay, so I don't know what that is. So that's what's happening in E. E, we're just being more specifically physical. Okay, so that's E. The derivative is negative a square root of k over m sine square root of k over mt, and then the second derivative is negative k over m a cosine square root of k over m times t. So the negative k over m comes out after we've squared it. So that is, that's Hooke's law. d2x dt squared equals negative k over m x. That's Hooke's law. Okay, you can stop, but that's all I feel like saying about that. Now here, so I'm believing John that we did not get up to this. F is important, is worth going over, and I don't think we really got to this on Monday. So, okay, so here we are in F of Roman numeral 1 of homework 2. It gives us this function x equals a cosine omega t plus 3.5. 3.5, what the heck is 3.5? 3.5 is just some arbitrary number. There's no significance to 3.5. It could have been 3.4, it could have been 17.9, or it could have just been the letter capital B. Like, it is literally just a number that does not change even while t and x vary. Okay, it's a number that doesn't change, i.e. 3.5, as it says here in the illegible blue, 3.5 just stands for some arbitrary constant value. Okay, that's all I know about. That's all I care. That's whatever I'm going to do with it now. It doesn't rely on any special property of the number 3.5. But one thing I know about this 3.5 or whatever number is being stuck into the parentheses there, it must be measured in radians for any of this math to work at all, right? I mean, first of all, please note that omega t is measured in radians. That is to say, omega is measured in radians per second, and t is measured in seconds. So the seconds cancel. And so omega t, the whole thing, is equal to radians. And the only thing you can add to radians are some more radians, right? You can't add a kilogram to a meter. You can only add a meter to a meter. Similarly, you can't add anything to a radian other than another radian. So that 3.5, whatever it is some constant measured in radians. It's all I know about it, okay? And I'm doing raw math. I'm just presenting myself with a function I just like walked up to at a party and I'm like, hey, how are you? Haven't seen you in years. What do you think of this function I got in my pocket? X equals A cosine omega t plus 3.5, right? I mean, that's obviously ridiculous. Like, what kind of party is that? But I'm saying, like, this is just a mathematical function that's not necessarily assuming any particular context or understanding. It's just a mathematical function that's sitting there. And I say in the question of the homework in part, I don't know why it's called F part 3. It should be called part 1, but it's called part 3. It just says, what's dx dt? What's the derivative with respect to time of that x function, right? So I do the same thing that I did in the prior exercises. Like, I recognize that it's a trigonometric derivative. I recognize that it's a trigonometric function, and I recognize that it's a function of a function. So I've got to use chain rule to do it. And so I'm going to slow down. So notice this now. So I've got to do chain rule. I've got to say that dx dt equals negative a sine of whatever's inside the parentheses, and then multiply that by the derivative of whatever is inside the parentheses. But now, please, like, let's all be together on this. What's inside the parentheses, like, used to be just omega t. Every day that we were doing this for 2 weeks, what was inside the parentheses was just omega t. Now suddenly it's omega t plus 3.5, right? And 3.5 is just an arbitrary constant. I've got to take the derivative with respect to t of omega t plus 3.5. What I'm asserting to all of you, what I'm saying, what I want to make clear and sort of explicit, important, is that the derivative with respect to t of omega t plus 3.5, the derivative of that expression is still just omega, right? Like, I think you all know that, but let's just make it absolutely clear. Like, in other words, technically the derivative is omega t plus 0. Sorry, technically the derivative is omega plus 0, right? Like, the derivative with respect to t of 3.5 is 0. Let me just make that super clear. Right? So our expression inside the parenthesis has changed. It used to be omega t. Now, for some reason that is unspecified, for some reason right. Thank you, John. And I really thank you. That is total participation. Please submit that for points. Like, and I'm not being sarcastic. I really want to applaud John here for saying that. Like, thank you for confirming that you're understanding what I'm saying, because I do think this, yes, I'm saying that 3.5 is just a constant. So I am taking the derivative of it. Like, I'm not ignoring it. I mean, this is why I appreciate that John just said that. I'm not ignoring the 3.5. I'm totally taking the derivative of it. But the derivative of it is 0 because 3.5 is just a constant. That is correct. So when I do the chain rule, what comes out is still just omega, right? Okay, so the 3.5 is there, and it seems to be changing the function, but it doesn't seem to be changing the nature of the derivative. So when I take the derivative, I get dx dt equals negative a omega sine omega t plus 3.5. Like, that's that part. So again, thank you, John. Yes, absolutely agreed. Now I go to the next step where it asks for the second derivative, d2x dt squared. So I take the derivative again. Okay, so I do the derivative of negative sine and I get negative cosine. And I've got to take the derivative of the inside again. But again, the derivative of the inside is just omega. So omega comes out again, and I get omega squared. So remember again, everybody, like, this is not a joke. Now, I mean, obviously it's not a joke. It's not funny at all. But I mean, this is not, I don't know if it's obvious or not. I don't know. I don't know if it seems obvious or not. But this is not a trick question, and it's not just some it's not just some minor point. I'm saying we're now playing with a new function. We're playing with a more complicated looking function, one that has something extra inside the parentheses, some extra number that's measured in radians. But apparently, when I take two derivatives of that, nothing weird happens. And if I look, when I take two time derivatives of a cosine omega t plus 3.5, I get back negative a omega squared cosine of omega t plus 3.5. So, which is x. In other words, does it say? Well, yeah. So I get back. So to answer question G, where G asks, is this new, more complicated function, is it a solution? And this is now the Maisha question, right, from Monday. Is this new function a solution to d2x dt squared equals negative omega squared x? The answer is yes, apparently, because this new function, even when we differentiate it twice, we get back itself times omega squared times -1 times a negative sign, right? So apparently, so the answer to G is yes. And here's why this is important. Like if 3.5 was, it wasn't the specialness of 3.5. It was the specialness of the fact that 3.5 is just some number, some arbitrary constant. So from now on, I'm going to say that 3.5 could be any number at all. And I'm going to use this symbol. I'm going to, from now on, and I think I make this clear on the next page. I think I'm about to make it more clear. But I'm going to use this new symbol that looks like a rotated theta, right? It looks like a theta that you turn on its side. So so it has a vertical line through it instead of a horizontal line. That symbol is a lowercase Greek letter called phi, or sometimes called phi. No one actually really does know how to pronounce it. I mean, anyway, I call it phi. That letter I'm going to use to stand for any arbitrary constant measured in radians that could be stuck into that parentheses. And evidently what we're saying is, oh, you wanted to remember, up until now, we've been saying the condition for simple harmonic oscillation is that differential equation. The solution to that differential equation is the equation of motion for simple. Let me say that again. Sorry, that was garbled. We've been saying that the condition for simple harmonic oscillation is that differential equation. Then we've been saying the equation of motion, the predicting equation, the equation we would rely on to actually predict where an oscillator would be when, is the solution to that differential equation. We've been saying that if you want to predict where an oscillator is going to be, you would use x equals a cosine omega t plus 0. We've been saying that describes harmonic oscillation. Now what we're apparently saying is, oh, it doesn't have to be plus 0. It could actually be plus any number. It doesn't have to be a 0 in the parentheses. It could be any number at all, and that would still satisfy the condition for simple harmonic oscillation. That's what we're saying here. So we're saying from now on, our solution to the differential, this is a real point that we're making. It's not just a random example. Like, it's not just a homework thing. We're saying from now on, we can stick an extra number in that parentheses that might be 0, but it might not be 0, and say that that whole extra complicated expression actually describes harmonic oscillation from now on. In other words, and then I'm going to turn the page, of course, but in other words, I'm saying that in other words, I'm not contradicting ourselves, but I'm developing something. We have been saying that we've been saying the solution is a cosine omega t. Now what I'm realizing is, oh, that was a solution. It wasn't the solution. When we've been saying a cosine omega t, when we've been saying x equals a cosine omega t, or however you want to say it, but we've been saying x equals x naught cosine omega t, or something like that, that's a solution. It's not the only solution. It's not the most general solution. It's a solution. Now I'm saying we can make a slightly more general solution. We can make a solution that's a little bit more broad and more complicated than that. We can include an extra number in the parentheses and call that extra number phi. Oh, excuse me for 1 second. Pause it. Hello, hello. Greetings, greetings. Hello, hello. Greetings, greetings. Teaching. So hello. I'll see you guys upstairs in a minute. Good to see you. Good to see you. Hello, hello. Hello, hello. Good to see you, teacher. Hello. Okay. All right. So I'm going to turn the page here. Okay. So I'm yes.
Can you get my stuff from not racist?
I will as soon as I'm done teaching. Yes, I absolutely will. Good to see you. Good to see you guys. Okay. So let me back up a page for a second. So yes. Oh, that's class participation. He says yes, he says hello too, or he did a minute ago. Or he would have. That's very kind of you all. Okay. Yes, I will tell him you said that. Okay. What was it? Oh, so this phi, that lowercase Greek letter phi. Oh, that's so sweet. Oh, I'm not telling his brother. Okay. That lowercase letter. Okay, you guys are too much. I can't handle it. It's a good thing that anyway, that lowercase Greek letter phi, it stands for phase constant. Okay, from now on, that extra constant that we're sticking in the parentheses, of which we are taking the cosine, from now on, we're going to call it a phase constant. We are saying that the solution to the differential equation for simple harmonic oscillation can include this extra term called a phase constant. That's what it's called mathematically. It's now my job to explain to you the physical significance of the phase constant. So let's turn the page, shall we? Okay. I'm going to tell you right now that I'm going to tell you what it means, but what it says here on the page is that the meaning of it becomes important. It becomes important once you have more than one oscillator. In fact, let me add a page here. Okay, sorry, let me show you quick. Oh, I'm going to look in the chat. I think the chat is all about blue. That's the only one you know. Okay, fair enough. Okay, all right, let me quickly explain. I'm looking at the time. Okay, here's the deal with this extra bit, this phi, this phase constant. Again, in the homework, the number was 3.5. The homework was just an exercise to show you how an extra number could be fit into the cosine function and wouldn't mess up the derivatives, right? Okay, again, there was nothing significant about 3.5. It could have been any number. So from now on, we're going to call that any number. We're going to phi, and well, we're going to use phi to designate that number. And phi stands for what we're going to call the phase constant. That extra number that we can put into the parentheses, it must be measured in radians, and it's called the phase constant. So what does this extra bit measured in radians do? Well, number one, what many of you may remember from math class or may be able to visualize is by sticking an extra number measured in radians into that parentheses, what that's doing is taking the whole cosine graph and it's translating it, it's shifting it to the left or to the right, depending on whether phi is positive or negative. Like you might remember that from math, and that's true. That's what it's doing. It's not stretching it, it's not changing the amplitude, and it's not changing the omega. It's not making more bumps per unit time. It's just moving the bumps left or right. That's what it's doing on a graph. What does that mean in physical reality? Well, what phi is, it's like a head start or a delay, depending on whether it's positive or negative. It's a head start or a delay, just as you might see in the graph. Like if you, it all has to do with where in the cycle this oscillating object starts. It's a head start or a delay with respect to the cycle, with respect to what we call the phase in physics. Physics means which part of the cycle are you in? Are you like at the top of the cycle, the beginning of the cycle? Are you in the middle of the cycle? Are you in the end of the cycle? Wherever you are in the cycle, we call your phase. Okay, kind of like phases of the moon, right? So let me be really specific about this for a minute. What we're really talking about with the phase constant is where the thing is at the, where in the cycle your oscillator is when the timing starts, when you start your stopwatch. Okay, so in the examples that we've been using up until now, when we haven't even had a phase constant, when we've been tacitly assuming that the phase constant was 0, we've been assuming, like homework 1, we've been assuming that the moment we started our stopwatch, the object, the oscillator, the mass at the end of the spring was all the way at the end of the spring, at its maximum displacement from equilibrium. We've been assuming, right, that when t equals 0 and v naught equals 0, the object was as far away from equilibrium as it could possibly be, the beginning of the cycle, so to speak. And indeed, if you think about it, like that's the case where phi equals 0. When phi equals 0, right? So plug it in your mind into, this is where I'm looking at the bottom of the page here. The function is x equals a cosine omega t plus phi. Well, if phi is nothing, if it's 0, then that means that when t is 0, right? So I'm sort of saying plug in two things. Plug in 0 for phi in your mind and plug in 0 for t. Then you'll have the cosine of 0, the cosine of 0 plus 0. You'll have the cosine of 0. Well, the cosine of 0 is 1, right? The sine of 0 is 0. The cosine of 0 is 1. So when phi is 0, then that means that at t equals 0, x equals a times 1, right? It equals a times the cosine of 0, which is 1. So that I'm saying if phi is 0, if there's no head start or delay at all, then when t equals 0, x is at the amplitude position. It's at maximum displacement. However, if phi were something like pi over 2, right, where the highest, now to be clear, we're not actually talking about a wave yet here. We're just talking about an oscillator. But yes, the highest. Yeah, John, I mean, good question, John. So phi equals 0 means that you're at your highest point at the beginning of timing at t equals 0. So I think I'm so highest, yeah. But see, if phi, for example, is pi over 2, oh wait, yeah, further, that's right. That's right. Furthest distance away from equilibrium. Good. Yes, that's what I mean. Good. Yes. Good questions. Points. Wait. Well, no. Wait, if it's a pendulum, it would be not the middle of the, well, it depends what you mean by wait. Okay. Thank you, private chat person. I totally see that. Cool. Wait, where it rests. Well, wait, that would be the middle of the, hold on. If it were a pendulum, if this is a pendulum, but a direct chat person, yes, totally got it. Cool, no problem. But John, good questions. Let me address these to everybody. I'm saying now, if you don't have a head start at all, if phi equals 0, then that would mean that that you started at the beginning of your cycle at the maximum point I mean, the maximum displacement from equilibrium. So if it were a mass on a, if it were like the question homework 1 mass on a spring, it would be starting at 15 centimeters away from equilibrium. And if it were a pendulum, to answer John's question, I mean, the timing would start when the pendulum's like all the way up here, like not in the middle, not where it rests. I don't know if we're saying the same thing or not, but to address John's question and to address what I'm trying to say, if we have a head start, if phi equals pi over 2, if phi equals pi over 2, now everybody follow this, I mean, including John. If phi were to equal pi over 2, what would that mean? It would mean that it would have a pi over 2 radian head start. Now, what the heck does that mean? Pi over 2 radian head start. Remember, everybody, there are 2 pi radians per every cycle. There's the key to remember to all of this is that there's 2 pi radians to every cycle. So pi over 2 radians literally means a fourth of a cycle, right? Like to everybody. Like I'm just using pi over 2 as an example here, but it's like a good example. Pi, always remember that 2 pi radians means a cycle. So pi over 2 radians would mean a quarter of a cycle. So if something had a quarter of a cycle head start, that would mean the thing that I think John is saying. If something had a quarter of a cycle head start, that means that when I started my stopwatch, it was already a quarter of the way into the cycle. It wasn't an amplitude position. It was like if it were a mass on a spring, it was already at the spring equilibrium position. If it was a pendulum, like John's example, it would mean it was already at the bottom place, that bottom place when my stopwatch started. Oh, good. Thank you, John. And that's totally closing a conversation. Totally submit that for points. Like, I'm glad that John, thank you for saying, okay, yeah. So to everybody, what I'm trying to say is this. Phi stands for a head start or a delay, like depending on if it's positive or negative. Phi yes. So like, yes, and I'm going to say that example in one moment, but yes, very good. I'm saying phi stands for a head start with respect to the cycle. The cycle in my mind, in our minds, begins at amplitude position. If you don't have a head start or a delay at all, if your phi is 0, that means when the stopwatch started, you were all the way at maximum displacement from equilibrium. If you have some sort of head start, some sort of phi, that means you're already somewhere into the cycle when the stopwatch started. If it were a pi over 2 radians, that would be a quarter cycle. So it would mean you're already at equilibrium when the stopwatch started. Or as John is saying, to pick up on his example, if phi were pi, if phi equals pi radians, in other words, if you had like x equals a cosine omega t plus pi, then pi is half of a cycle because there's 2 pi radians for every cycle. So pi would be half of a cycle. And as John's saying, that would mean you're already over here on the other side when the stopwatch starts, right? Totally correct. So phi measured in radians is how much of a head start or a delay we have with respect to the cycle. What kind of portion of a cycle we're already into when the stopwatch starts. Okay, that's what phi means. Phi, the phase constant is where you are in the phase when the stopwatch starts. Now it's a constant. It is a constant. It's not a variable. So it's like, it is just literally your head start or your delay. Like once you have it, that's what your head start was for all time. It doesn't mean that you stay there for all time, but it means for all time, that was the head start that you had. Okay. Now, it's up to us to decide when to start our stopwatch. We can start our stopwatch whenever we want. So the truth of the matter is, we want to start our stopwatch whatever's most convenient and natural and easy for us to measure things. So generally, the reason we haven't even mentioned phase constants until now, the reason we haven't even ever added this extra term is because it was totally not convenient to, because up until now, we could start our stopwatch wherever we want. So of course, the most natural, easy place to start a stopwatch is like in the lab, like you let a pendulum go back and forth for a while, you get it going, and then you start your stopwatch as soon as the pendulum is like all the way at one endpoint, because that's where it stops momentarily and starts going the other way. Like, it's the easiest place to start counting cycles. If you only had one oscillator, what I'm saying is this: if you only have one oscillator, you can start your stopwatch wherever you want, and it's generally most convenient to start it at the amplitude position. So it's generally most convenient to have a phi of 0. So up until this point in the class and in our thoughts, we haven't had to deal with phi. There was no reason to, because we could just sort of make it 0 whenever we wanted, and that worked. Why would we ever, in other words, the question arises, why would we ever bother with this phi thing? Why would we ever even start something in the middle of its cycle? What's the point of that? And the answer is this: a very important question, a very important answer. The answer is there's no point ever in having a phase constant that isn't 0 unless we have more than one oscillator, which we're totally about to have. Okay, if you just have one oscillator, you do whatever's convenient for that oscillator. But if you wanted to have more than one oscillator doing different things, then even if you started one oscillator over here, then the other oscillator would not start over here. So some of your oscillators, you have to track where they are in the cycle relative to your first oscillator. In other words, the phase constant becomes very important and necessary as long as you have multiple oscillators doing different things. And the very next thing that I want to look at in the class, or that something that you have begun to look at in lab and stuff, is I want to look at what happens when we have multiple oscillators doing different things. It's very important to look at that. You'll see if you'll see why. So we're going to turn the page. Right. Okay. So it says phase constants become important with multiple oscillators. That's what we want to look at now. I'm just looking at the time. Okay. So what I want you to do now, clear your mind or whatever. And I'm going off homework now. Like, I'm using this homework question to explain a large concept that we need and that you need in lab and so forth. So like, you could put your homework to the side for the rest of this period. I want you to imagine the following. I want you to imagine a bunch of identical vertical oscillators. So I want you to imagine a bunch of oscillators, a bunch of masses on springs, each identical spring, each identical mass, K, 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 M, 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 M. And so each one of these oscillators, since they have the same K and they have the same M, I want you to imagine that each of these oscillators, therefore, has the same omega. Each one of these oscillators is going to oscillate up and down at the same rate as every other oscillator. That's what I mean when I say they're all identical oscillators. Let's even assume that they're all going to oscillate with the same amplitude. So like, they're identical oscillators. I want you to imagine them, and I'm going to draw a picture in a minute, but I mean, the next page, there'll be a picture. But I want you to imagine that these oscillators are vertical oscillators, like they're each going to oscillate along a Y axis, up and down. They're going to change their Y position. But there's many of them. Let's imagine that there's many of these oscillators, and let's imagine that we arrange them along a horizontal axis. So we take multiple vertical oscillators, but we arrange them along a tabletop or a lab table or something. So we've got vertical oscillator over here, and then next to it, vertical oscillator here, over, and then vertical oscillator over there. Furthermore, and again, believe me, I'll give you a picture of this in a second, but I think, but furthermore, I want you to imagine that these oscillators are equidistant from one another. So you could be really specific here and say, sorry, you could say, in fact, I will, let me just see if I do. Yeah, let me draw a better picture than that right there. Hold on. This is what I'm saying. Okay. So what I'm asking you to picture here, right, is you have all these identical oscillators, the same K, same M. They're all free to vibrate, oscillate vertically. But then we place, and it goes on and on forever, this arrangement. Not forever, but I mean, it goes on for a really long time. And imagine that we place them along an x-axis, and we place them equidistantly, so that in fact, the leftmost oscillator we're going to place right on the y-axis, right at x equals 0, right? And we're going to call that the 0th oscillator. Then at the very first x position, at like 1 meter to the right, we put what we're going to call the first oscillator. And then at the 2 meter position, we put the second oscillator, et cetera. Okay. So we're putting one oscillator like at every meter, and we're letting the vibrate. Okay. Now they're all going to oscillate at the same rate, and they're all going to oscillate with the same amplitude. But let's imagine further, and this is what it says here on the page. Imagine that they're equally spaced, but they're all staggered in phase by a constant step. That's what it says here. Imagine that they're all staggered in phase by a constant step. What do I mean by that? I mean, like imagine this. So what I want you to imagine is that each next oscillator has a delay or a head start of pi over 2 radians compared to the one next to it, right? Like, and pi over 2 is just an example, but it's the example I did a minute ago. Pi over 2 is a quarter of a cycle. Right? So, oh, very good. I would actually say that this is a transverse wave. This is going to be a wave. Yeah, I mean, he's way ahead of me. Yes, I think what we're doing here is building a wave. Yes, I think it's a transverse wave, not a longitudinal wave. I think this is ultimately going to be like the wave that you did in lab 3. But yes, very good. Yes, right. Well, actually, let me let me totally agree with that. I'm saying if all of these things are doing the same rhythm between the same 2 endpoints, but they're all doing it staggered. Like if when we start our stopwatch, the very 0th one is at the amplitude position down here, or the negative amplitude position. And the very first one is right there at equilibrium. And the very second one is at the positive amplitude position. Yeah, very good. Very good. No, John's totally right. He's totally on this. And he's not off the point either. Like, this is the point. Like, if you were to set this thing in motion, if you were to set up this collection of staggered oscillators, what you would see rippling horizontally would be a wave pulse, right? Like if they're all going like this in the correct rhythm, you would see like a hump of springness. You would see like a crest ripple from left to right. Like first the leftmost springs would be all the way on the top, and the next ones would be down below. But then the leftmost ones would be down, and then this one would be up, and then this one would be up, and then it, right? So we would see pulses rippling from left to right to right to left. Absolutely. The punchline being, I mean, qualitatively, what we're saying here is, what is a wave pulse? A wave pulse is a collection of phase staggered oscillators, or put another way, a collection of identical oscillators that are staggered in phase by a constant amount is what a wave pulse is. Now I want to say a lot. That's in English, like that. Like this is lab 3 from another perspective. But I want to talk about the math of it. But yes, that's very good. So let me be mathematical about this for a second. I'm saying each one of these oscillators could be expressed by its own individual oscillating equation, right? Right. So like, and again, I'm using pi over 2 radians per every meter, or pi over 2 radians of a phase per every next oscillator. Or in other words, that each oscillator is a quarter cycle out of step with the one before it. I'm just using that as an example. We could do any constant phase step that we want. It's just easiest to visualize pi over 2. So if we're using the example of pi over 2, what we would find is the very zeroth oscillator could be captured by the equation y sub 0 equals a cosine omega t plus 0, right? The very first one, we say we start at the low amplitude position, right when our stopwatch is at 0. At that very moment, the next one is pi over 2 ahead of the first one, right? But the very next one, the very next oscillator, is pi over 2 ahead of the one before it. So it's 2 pi over 2 ahead of the 0th one, right? So in other words, this one. And y over 3 yeah, pi, but what about pi? Oh, that's nice that you can, I don't know how you did the pi in there. That's cool, but what just happened? Wait, sorry. Oh, good. Yeah. Oh, good point, John. Yes, he's all over this. Yeah. So I see what you're saying. So the very first one is pi over 2 ahead of the 0th one. So the second one is 2 pi over 2 ahead of the 0th one. And yes, you could reduce that fraction and say that the second oscillator number 2, is pi ahead of the 0th one. That's right. But I'm going to leave the fraction the way I wrote it for the moment because I want you to see a pattern. But yes, John is totally right. I'm just going to go one more step in the pattern. You see that every next oscillator could be written with its own equation that's sort of predictable and easy to write. Like, even if I don't keep writing this whole list forever, if I just went up to you and said, all right, what's the equation for the 17th oscillator? You would know right away that it's y sub 17 equals a cosine omega t plus 17 pi over 2, right? It's like, in fact, I'll say, right? So in other words, y n equals a cos for any given n, right? But I can, right? I'm just going to summarize. So right, like you name the oscillator, you know exactly what equation will describe it. It'll be a cosine omega t plus whatever number that is times pi over 2, because each one is pi over 2 relative to the last one. But we've arranged these oscillators on purpose along an x-axis. We've deliberately placed them equidistantly along some horizontal meter stick or something like that. So whatever oscillator we're talking about is always, we always know exactly where to look to find it. Like the 0th oscillator is right at position x equals 0. The number 1 oscillator is at x equals 1 meter. If you wanted to know what the 17th oscillator was doing, you would know to look at x equals 17 meters, right? Like that's where it's going to be. We're putting one oscillator at every meter. So x always equals n. Whatever number oscillator we're talking about is the position that we look. Therefore, what I'm saying so far is we can capture this entire arrangement with one equation, it seems. We can capture with one equation that says y equals a cosine omega t plus pi over 2 times x, where x is where you're looking on the horizontal axis, right? Like if you're looking at if you're looking at the 17th oscillator, that means you're looking at the 17th mark on the horizontal meter stick. You're looking at meter number 17. And that oscillator will be 17 pi over 2 radians ahead of the farthest most oscillator, the edge oscillator. It will be, in other words, 17 half cycles ahead of the edge most oscillator, right? And so if ever you want to know how high, if someone walks in and says, hey, how high is the spring material? How high is the mass? We would say to that person, well, wait, that's kind of a vague question. I mean, there's a lot of masses doing a lot of things. There's a lot of masses at a lot of different heights at a lot of different times. But if you want to ask me, how high is the mass? Well, you got to specify two things. Tell me, when am I supposed to look? And tell me where to look. But if you tell me those two things, if you say, how high is the mass at this moment in time when I'm looking over there at that spot, oh, then there's one definite answer to that question, right? If you specify time, well, relativity, I'm not sure that not good, not relativity in like the Einstein sense, not crazy relativity, but just, I'm not sure, but, oh yes, yes, I see what you're saying. Yes, every single one of these, yes, all of this is measured relative, that's good. All measured relative to the oscillator right at x equals 0, right at the y-axis. Yes, like it has no head start or delay whatsoever. So all head starts or delays are being measured relative to it. Yes, that's good. That's true. Yes. So if anybody ever wants to know how high is a mass, we would say to them, well, you got to specify two things. You got to tell me when to look and you got to tell me where to look. But if you tell me what moment to look and what horizontal position to look, then this I can plug into this equation and it will tell me exactly how high that mass will be. It's saying y is a function of time, and it's saying vertical position is a function of horizontal position and time, right? That's what this is saying. Now let me go one step further. Okay, what I'm saying here so far is we're almost done developing a very important equation. We do have an equation here, but we're not done with it yet. The equation we have here is y equals a cosine omega t plus pi over 2 times x. Pi over 2 times x. What's pi over 2? Pi over 2 is just an example, right? It means a quarter of a cycle, but it was some amount. It could have been any portion of the cycle. But what was it representing? Remember, it's pi over 2 was being multiplied by x to tell us the phase constant for any particular oscillator that we're looking at, right? Pi over 2 in this example was the constant amount by which pi over 2 in this example was the constant number of radians per each meter that we advanced along the horizontal axis, right? We're saying, remember, the whole thing inside the parentheses has to be measured in radians, right? Like, remember, omega times t has to be radians, so you can take the cosine of it. And remember, anything you add to omega times t has to be in radians. So this thing said pi, it doesn't say that the phase constant for every single oscillator is pi over 2. It's saying it's pi over 2 times the number of oscillator that you're talking about, right? It's saying if you're at the 15th meter mark, if you're talking about the 15th oscillator, then your phase constant is pi over 2 times 15 meters, right? That's what it's saying. So the pi over 2 is a number that's representing the phase advancement per, it's pi over 2 is how much more radians you're adding for each new meter that you add as you walk along the x-axis. In other words, pi over 2 is not measured in radians, it's measured in radians per meter, and then multiplied by x, which is measured in meters, so that the meters cancel out and you end up with just radians, right? Like, does everybody notice that? So pi over 2 could have been any number at all, as long as that number was measured in radians per meter. So I'm saying that pi over 2 number in this case, the pi over 2 number represented how many extra new radians we get for every extra new meters. It's like if you made a graph of phase constant as a function of meters, you would find that that's a straight line graph. When you're at 0 meters, you get 0 phase. When you're at 1 meter, you get pi over 2 phase. When you're at 2 meters, you get 2 pi over 2 phase. The rate of change of phase per change in meters is a constant, right? The slope of that graph would be a constant. That constant, which in this case is pi over 2, that constant must be measured in radians per meter. That could be any number at all. The name that we give that number from here on in is called K, as in that number that you used in lab 3. K, which is measured in radians per meter, is called angular wave number. We're saying if you want to capture this whole collection of phase staggered oscillators, if you take a whole collection of identical oscillators and then stagger them in phase by a constant amount, the entire collection could be captured in one equation written like this. And this on the one hand is a collection of identical oscillators staggered in phase by a constant amount. On the other hand, the reason that K, that number is called angular wave number, is that what this produces, as John said correctly, 15 minutes ago is this is a wave, right? This is a wave. A wave is cosinusoidal oscillations in time superposed on cosinusoidal oscillations in space. A wave pulse is oscillations in time with oscillations in space at the same time. That's what you were finding out in lab 3, only you took a wave pulse and dissected it. You looked at a wave pulse, took a movie of it, and looked at, and then excerpted from that movie 2 different sets of data. Y as a function of t, and you got cosine. And then you looked at y as a function of x, and you got cosine. You looked at a wave pulse and found that it was oscillation. You looked at a wave pulse and found that it was oscillations in time staggered throughout space. What I'm saying is that if you create oscillations in time and stagger them through space, you'll get a wave pulse. A wave pulse is oscillations in time oscillating through space. Or you could say it's an oscillation in space oscillating in time. Oh, I'm saying ultimately that this angular wave number K that you dealt with in lab, K is to space. And this is not the K of Hooke's law. This is a different K. I'm sorry that they're both called K, but this is a different K. K is to space as omega is to time. K is radians per meter. Omega is radians per second. Radians per second multiplied by time to get radians per second multiplied by seconds to get radians. Radians per meter multiplied by meters to get radians. Omega is the rate at which each individual oscillator goes up and down. K is the rate at which the cycle of oscillators, the pattern, repeats in space. Do you see what I'm saying? Let me say this one other way. I am not saying that an oscillation is a wave. An oscillation is not a wave. I am saying that in order to understand waves, the crucial ingredient that we must understand is oscillation. The reason we've been spending so much of our energy in class on harmonic oscillation is that harmonic oscillation is the fundamental ingredient to a wave pulse. A wave pulse is not an oscillate. This is not a wave pulse. And a picture of a wiggle is not a wave pulse. A wiggle is not a wave. An oscillation is not a wave. But an oscillation wiggling is a wave, or a wiggle oscillating is a wave. A wave is time oscillations oscillating through space. It's cosines in time being cosine through space. That's why not the 2? It is the 2. Wait, because no, wait. I think I just, so I'm saying in order to have a wave pulse, you've got to have 2 oscillations, two sets of oscillations in time and oscillations in space. If I just draw a cosine graph, that's not a wave. If the cosine graph is going up and down in time, then it's a wave. Or if I just look at an oscillation, that's not a wave. But if I have multiple oscillations that are all staggered this way, then that's a wave. A wave is oscillations in time and in space. Okay, got it. Okay, got it. Okay, but this is kind of a big point. So let me put this one other way, and then we'll stop for today. But hopefully you get it. But this is what you found in lab 3. You found this is the superposition of the 2 cosines that you found in lab 3. You found in lab 3 that if you pick any one horizontal position from your movie in lab 3, right? If you just look at any one horizontal position and make the red dots going up and down, if you pick X and you hold X as constant, you find that Y as a function of T is a cosine graph, that the height of the wave oscillates up and down harmonically as a function of time if X is fixed. Similarly, you found that if time is fixed, if you picked any one snapshot, any one frame of the movie, and just let your eye go from left to right across the x-axis, you found that the height oscillated cosinusoidally. So if x is fixed, y as a function of t is cosinusoidal harmonic oscillation. And if t is fixed, then y as a function of x is cosinusoidal oscillation. Put together the two, and you have a cosine of time and space. That is a wave pulse. That's what this is. Oh, and lastly, please note this super kind of obvious, but kind of not, this super important fundamental characteristic of wave motion. When I say that, if you set up this whole collection of staggered oscillators, when I say that you make a wave pulse, actually, John Ford, this is all transverse that I'm talking about. This is all transverse. And let me show you what I mean. I'm saying once you set this whole thing up, and so the first thing is going up, down, and the next thing is going up, down, and the next thing is going up, down. And so then you see this pulse travel along. What I'm saying here is that your long string in lab 3 was in effect this. I'm saying that one little piece of the string was going up, down, while the next piece of the string was going up, down, while the next piece of the string was going up, down. So each one was oscillating harmonically, and their oscillations were all staggered in phase. But what's fascinating about this, what's so cool about creating a wave pulse in the end, the deal with a wave pulse is once you see that pulse travel, when a wave pulse, when a crest, if you like, or a trough or whatever, when the pulse propagates, travels from one end of your long string to the other. So like in lab 3, when one person stood over here and the other person stood over there, and you shake the string, and so this hump travels from A to B, something has clearly traveled. Like, it's traveled a certain distance. You could time it with your stopwatch and see how much time it took to travel. You could divide the distance by the time and get the speed. And you can make predictions like, oh, if it traveled at 340 meters per second, then I guess in 2 seconds, it'll travel 680 meters or whatever. Like, you could definitely observe and measure some entity traveling according to all the rules and the analyses of physics, right? But there's no individual thing in the world actually traveling. That is, when a pulse travels along the string of lab 3, something definitely travels from one end of the string to the other. And for sure, things are moving. Spring is moving. If you have a long spring of metal and you shake it, for sure, a pulse travels from you to your partner. And for sure, what's moving is metal. Metal is moving over here, then metal is moving over here, then metal is moving over here. But there's no individual piece of metal that ever goes from you to your partner. In other words, what's fascinating about a wave pulse is that it is physical motion, but it's not material motion. I'm saying, and we're going to end right here, but let me just say this clearly. I'm saying this is unthingy motion. Wave motion is fundamentally real, but fundamentally unthingy. It's immaterial. I'm saying wave motion is immaterial. There is, when a wave pulse travels from me to you. Yes, that's right. That's good. Yes, that's good. Very good. When a wave pulse travels from me to you, something travels from me to you for sure, but no thing travels from me to you. And I'm going to use like John's example, but I'm going to take it one notch down. Like literally sound is a perfect example of this. When I shout at you, for sure, sound goes from my mouth to your ear and you hear it, like it's undeniable. And you can time how long it takes for it to get to you, and you can measure the distance that it took to travel to you, like something real, non-magical and scientific. Okay, so hold on a second. Sorry, just hold on a second, because we're just sorry. For sure, you can hang out after class for 1 second. Let me just say this to everybody. When I shout sound at you people, for sure, something is traveling from my mouth to your ears. And if we break it down and analyze a little bit, what we might find is that air molecules are doing the motion, but there's no individual air molecule that goes from my mouth to your ear. Wave motion is fundamentally immaterial. If I shout at you, air is moving, but no air goes from me to you. That is quite fascinating to me. And the equation that describes this situation is what we just wrote. Y equals a cosine omega t plus kx. The motion that's happening is lots and lots of little harmonic oscillations in lots and lots of neighborhoods. And what ends up traveling is a pattern, not a thing, but a pattern. Okay, I'm going to hold it there. That's very good for everybody. I think you do get it. I think it's awesome. I know there are a couple of questions in the chat. I saw that. I mean, including John, including Maisha's. I don't want to blow them off. I think they're great questions. So I'm going to hang here for a second and answer, but I'm going to turn off the recording and everybody can go. I mean, have a great weekend, a great week. But if you did have a question or you still have a question, just hang on for a second and I totally will answer it. I just don't want to keep anybody past the bell. So thank you. Awesome. Have a great weekend, everybody. But hang on, John and Maisha, or anybody else who has a question. I'll be right with you. Hold on 1 second. Let me just turn off the recording.